All right, our last test out of 10.4. So we now have the divergence test, which is our go-to. We have the P-series test you can just look at to determine if it converges or diverges. And lastly, we have this integral test. All right, so here's our integral test, which is theorem 10.11, which we all know is bogus, but I'm going to write this out. Suppose f, so a function f, is a continuous, positive, decreasing function for x greater than or equal to 1, and we are going to let a sub k equal f of k for k going from 1, 2, 3, etc. Then this series, k going from 1 to infinity of a sub k, and this improper integral from 1 to infinity of f of x dx, either both converge or diverge. In the case of convergence, the value of the integral is not the value of the series, equal to the value of the series. Okay, so here's our integral test. Suppose my function f is a continuous, positive, decreasing function for x is greater than or equal to 1, and we want to let my a sub k equal f of k for k going from 1 to infinity by integers, right? Then my series here and my improper integral either both converge or diverge. If they do converge, the value is not the same. Literally, we're back to that same thing. The only thing we are determining is convergence. That's it. Not the value. The only time you get a value of a series is if it is a geometric series or a telescoping, right? That's not what the integral test does. Now, here's the kicker to the integral test. You have to meet these three criteria. Criteria 1, criteria 2, criteria 3. Your function has to be continuous, has to be positive, and has to be decreasing for all of the values x greater than 1. If that happens, then we can look at the improper integral. If these criteria are not met, then you got to come up with a different way to do this. Then this is not your game. The integral test is not the test to use. You just have to come up with a different test, right? So it's the same. I know I keep making this comparison, but it's so true. This is the same kind of deal. Remember how many times I asked you, what are the defining characteristics of this problem whenever we were integrating? We're going to be asking the same question, y'all. What are the defining characteristics of this series? So I know which test to try to implement. All right? It's just a whole bunch of different tests to just simply determine convergence. Okay. So let's do this. Oh. And here's the other thing I want to say. So they either both converge or diverge. That's why whenever we did our integral test, we determined if it converges or diverges. Remember that there at the end? Now, basically all that's happening here is you're going to get same behavior. That's what's happening right here. The integral test just determines same behavior. You hit those three criteria. You have to show those three criteria. Then you integrate, and whatever your improper integral does, it is same behavior for your series. All right? Well, let's do some. Here's our first one. Let's go black. Example 2a. if I have this series, we're determining convergence. K is going from 1 to infinity of k over k squared plus 1. First and foremost, we check out the divergence test, right? Immediately do that. If I look at this, the divergence test, what does this limit go to? 0. You see that? I have a bigger degree in the denominator, so then this limit goes to 0. Well, the divergence test is out. So now we come up with something else. We're going to use the integral test for this one. So with my integral test, I have to meet those 3 criteria. With this 3 criteria, it has to be positive, decreasing, and continuous. Those may be out of order. I don't know. What did I say before? What was it? Continuous, positive, decreasing. Yeah. 1 and 2 are out of order. That's okay because it's just the criteria met. For x greater than or equal to 0. Now look at this. Is this going to be positive? Now keep in mind the criteria for this is for, sorry, I keep going back and forth, for the x values that are greater than or equal to 1. Yes, down here it's always positive no matter what because that's squared. But up here it could be positive or negative. However, I'm going for the values that are greater than or equal to 1. So yes, for the x that's greater than or equal to 1 because I'm looking at this f of x is equal to x over x squared plus 1, right? The same thing. Continuous. Is there anywhere that my denominator could equal 0? No, right? This is squared, so it's always going to be positive. If I add more positive to that, there is no possible way this denominator is going to equal 0. Yes, the denominator will never equal 0. Is it decreasing? Yes. The denominator grows faster than the numerator, right? Another way to determine decreasing is if you were to take the derivative of this, right? The first derivative. If the first derivative is negative, you know that that's also decreasing. Okay, those are my 3 criteria. Now, when you lay out these criteria, you got to give me something. If you just write yes, 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 I don't know that you know that. You could just be writing it because that's your Pavlovian response. So you got to give me a little bit here whenever you write that out. Remember, this is a proof that we're trying to come up with. Once these 3 criteria have been met, I can now integrate from 1 to infinity of x over x squared plus 1 dx. Now, guys, if you choose to keep this in terms of k, I don't care. Just put that dk back there. The proper way to do it is to make this all in terms of x. I don't care. I don't care because it's not going to affect anything. So if you leave all of this in terms of k, that's up to you. I just want to put that out there. All right. With an improper integral, though, we have to look at limits. So whenever I take this limit as, I just get in the mode there, don't I? The limit as a or b in this instance, because it's on top, I don't really care. I'm just going to leave it as a. Approaches infinity, I'm going to go from 1 to a of x over x squared plus 1 dx. Now, take a look here. What is my go-to method of integration? U sub. Do you think you can do a U sub on this? Yes. Why is this a U sub versus inverse tangent? Because there's an x on top. If this were just have been a number like 1, bammo jabammo, right? There's inverse tangent straight up. But the fact that I have an x on top, it's 1 degree less, then that's going to be a sweet little U sub. Good. So u is x squared plus 1. Du is 2x dx. So I know I've got this 1/2 du. Takes out my x dx. At x is equal to 1, u is equal to 2, right? Because I'm plugging this 1 in here. 1 squared plus 1 is 2. at x is equal to a, u is equal to a squared plus 1. So let's plug it all in. I'm going to scoot this up a little. I'm going to now integrate my limit as a approaches infinity from 2 to a squared plus 1 of, oops, I almost forgot my 1/2 in front, of 1 over u du. So I have my limit as a approaches infinity of 1/2 natural logs of u evaluated from 2 to a squared plus 1. I'm going to bring this right up here because I run out of room. So I have my limit as a approaches infinity of 1/2 natural logs of a squared plus 1 minus 1/2 natural logs of 2. Now, what do you know what's happening here at this a squared plus 1? What's that going to as a approaches infinity? Yep. So infinity minus some number is always just going to be what? Exactly, right? Exactly, infinity. So what do you know about this integration? It diverges. So because this diverges, I know that I have the same behavior. Therefore, the series, oopsie daisy, also diverges by the integral test. Right? Because my integral diverges with the integral, then my series also diverges. And take a look at this. I'm not getting crazy on your integration, right? We're not going to do that. I'm not too worried about that kind of stuff. I just want to make sure that you know how to work out some of these things